Section 10.2, there's a lot of work in this. We're going to look at the parametric, the calculus of parametric curves, and from there we're going to move on to polar. Over here we have basically the two equations, one we've used before, which is this one, which is how you find the derivative of a parametric curve. And you differentiate the y with t and the x with t. What I haven't shown you is that this is how you can integrate a parametric curve, and we'll show you that after I've done my intro question. So my intro question is question 5. So it's a pretty standard type of parametric equation. You've got x equals t squared, take away 4t. You're given that y equals t squared plus 4t plus 1, and you're being asked to find the equation of the tangent line that passes through that point, 0, 33. Well, before we actually find the derivative and then get the slope of the tangent line and so on, there is a little problem. This is the point that we're going to find the equation of the tangent line. But this is the, the xy coordinate of the point. What we don't know yet is what is the equivalent t value that would generate that point. So I need to know, is it t equals 2, is it t equals 10? Because I need to know what t is equal to, because once I get this derivative, won't everything be in terms of t? And I need to know what number to plug into here to get the slope of the tangent line. So it's a
4.
Whoa, impressive. Now explain it.
Algebraically, the t squared minus 4t, 4 squared minus 4, 4. And t squared plus 4t plus 1.
Okay, so if I've got you correct, which sounds good, if we just look at the x coordinate, which is 0, and you factor it out, there are only two values of t that would give you an x coordinate of 0, right? And if you then plug this one in, you get a y coordinate of 1, so that's no good. And if you plug this one in, you get the y value of 33, and there we got it. Kind of paraphrasing what you said, is that essentially what you did?
I get more guess and check style.
Okay, so we're looking good at this now. We're ready to move on. So I'll put a little squiggly line to separate it. So I'm now going to find the derivative, and it's dy by dt on the top, and the derivative dx by dt on the bottom. If you differentiate this guy, you get 2t plus 4. If you differentiate this guy, you get 2t. Oh, interesting. Take away 4. And to get the slope of the tangent line, we evaluate the derivative at t equals 4. So it's going to be 2 lots of 4, add 4. 2 lots of 4, take away 4. So that's 12 over 4, which ends up being 3. And then we use the point slope equation to get the equation of the tangent line. So it's going to be y take away 33. The slope, x take away 0. And that gets me 3x plus 33. And now we have the equation of the tangent line. And if I had time, couldn't I put that into Desmos and also put this into Desmos? And when I say a really nice tangent line at the coordinates 0, 33. So what that would be in the y-axis. I know this isn't the answer, but can you imagine that's where 33 is, right? And the thing looks like that. Wouldn't that be my tangent line? That kind of thing, at least. And you would only really worry about doing that in a test situation because you have a limited amount of time to do homework. You can't keep going back to Desmos. Plus, doesn't WebAssign tell you if you're right, so it's not hard to check. Are we comfortable about the derivative? It's actually I think sort of intuitive, isn't it? That formula, it kind of makes sense why that would get you the derivative of a parametric. What's less obvious is our next guy, which is how do you find the integral
I see that
of a
last page.
parametric?
There's something I was trying to write down at the bottom.
Listen, right. So how do you find the integral, right, of a parametric curve? And it's from t equals a to t equals b of y times x dashed of t dt. So it's only got the derivative of the x, but the untouched y, right? Now, to try and explain where that formula came from, it's okay to move this now, right? To explain where that formula came from, if I went and set out a normal integral in the good old Cartesian format, wouldn't it look like that? Now, actually, isn't f of x just y? So you could have written it down as y dx. So far, so good. Now, if you take dx by dt, right, and you look at that guy, you would call him x dash t. Great. That'd be a notation for it. Now, if you ever done one of those like in U subs where you move things around a little bit, won't dx be x dash t dt? So what we have is the y function in terms of t. Instead of dx, we have x dash t dt. So does that formula look a little bit less magic, and you kind of sort of see where it's coming from, right? So how do you use it? It's mostly plug and chug. So let's show you a pretty straightforward example of that. Suppose I have a parametric curve 7 sine t. This is version equation 6. And a sine t, a cosine t. And I want to find the integral of this parametric curve going from 0 to pi upon 2. Well, the integral will be from 0 to pi upon 2. This guy, that's basically y of t, times the derivative of this guy, dt. So this here is y, and this here is x dashed. Are you comfortable where the pieces came from? All of y times the derivative of x dt. And this now becomes 0 to pi upon 2, 7 sine t cosine squared t dt, which means you have to bring Calc 2 into it. How am I going to integrate this? Anybody got any suggestions about how I should integrate 7 sine t cos squared t?
Using the trigonometric identities, you can break up the sin and the codes.
You could also use substitution.
Could also use a U substitution. I think if you try to do a trig identity in that, you could certainly move things around. I've got a feeling, unless there's one I've missed, which I could easily
What about the integration by part?
Ooh, no. I like U subs. Integration by parts would be pick somebody to be F and somebody to be G, and I do not like trig equations to ever do integration by parts. And the reason I don't like those is that when you do the formula, the next bit, you get a bit and then you get a minus and an integral. The integral you get is just the same or uglier than the one you started with. And the whole idea of integration by parts is things should get simpler. So I would use integration by parts if it was 7t cosine t, right? If it had at least a power, because that power would eventually disappear and you could get your answer. We still have one more question, since it is going to be a U sub. Who is the U sub going to be? And that again is a big decision, because there's only one that works. What would the U sub be?
U is
Sine.
cosine.
I'm going to do it for cosine. Now, if you differentiate with respect to t, and differentiate a cosine, you'll get a negative sign. If you do I call the crossover, du then is going to be negative sine t dt. And then if you isolate the dt, you get negative du over sine t is dt. So I'll go over here and I'll leave the 7. And for the time being, although it's going to disappear soon, I'll leave that. That guy can be u squared, and the dt can be written as that guy. And then these cancel, and you're essentially going to integrate negative 7 u squared du. Are you comfortable with what we've got so far? Okay. Now, power rule. Add 1 to the power, divide by the new power. Some people do a substitution that I don't, substitute back. What I like to do is convert back to the t's. Now, once I do that, I can then evaluate at t equals 0 and t equals pi upon 2. And to me, that just is easier to do. So it's going to be negative 7/3 cosine of pi upon 2, basically cubed, because that looks nicer. Take away negative 7/3 cosine of 0, also cubed. Cosine of pi upon 2 is nothing, so all of that is 0. 2 negatives make a plus, and the cosine of 0 is 1. 1 cubed is still 1. 2 negatives make a plus, and the answer I got would be 7/3, which is correct. So you're going to integrate, you're going to have to do U subs, you're going to have to do power rules. You definitely sometimes are going to do integration by parts, not this particular time. You might have to do identities. I can imagine questions where you could play about with the thing, turn it into something nicer, using trig identities. And not just with trig functions. Obviously, if it's other functions, you do the same types of things, and eventually you get the answer. Now, next one is kind of visual. So I'm just going to draw what I can see. We're being asked to, again, find an integral. It's going to be sine squared t, and the y is going to be 5 cosine t's. Wait a minute, have I just done that? No, I haven't. Okay. It looked very similar. And you are given essentially the picture of the curve, and this guy here is at 1, and this guy here is at 5, and this guy, oh good, is negative 5. And we're being asked to find that area, because isn't that one of the things that an integral tells you, right? It tells you the area under a curve. In this particular case, we're going this way, right? So all I need to do here is find one really important piece of information. Don't I need to know the value of t to start and the value of t to finish. Agreed?
My old professor, he would like have us put a 2 up front and then just go from 0 to 1.
Put a 2 up front.
Of the interval and then go from 0 to 1.
Oh, so I got you. So you're thinking, why don't I just get that and double it?
Yeah.
Yeah, that works. I mean, so my integral is now going to be 2 somebody to somebody, right? Now, what you might think, and it may be the case, that it's going to be 0 to 1, right? But remember, we have this thing going on, right? So that's a little bit trickier.
Should it be a pi with a 2, right? Because the circle that usually go with a pi.
Okay, but let's pick that point. That point is sine squared t, because that's the x coordinate is 1. And that point is y is 5, well, x is equal to that, and 5 cosine t, and that's equal to 0. So if I wanted to find what that point was in a parametric, wouldn't I have to find a value of t where the sine squared of t was 1 and 5 times the cosine of t was be 0? That might be what you're saying. What is the unique value of t that makes both those things true? For what value of t is sine squared t1? And for that same value of t, will you get a cosine of 0? Where does that happen?
Pi over 2.
Pi over 2. Now you want to check it out. Sine squared pi over 2 is number 1, because that's what sine pi over 2 is, squared. So 1 squared is 1. 5 cosine pi upon 2 is 0. So I have found that guy, right? Now, how about that guy? Well, if I wanted to find the coordinates of that guy, wouldn't the x coordinate be 0 and the y coordinate would be 5? Agreed? And the x coordinate of 0 means that I need to find a value of t that makes that 0. And if the y coordinate is going to be 5, then don't I need a value of t that makes that happen?
Pi. 0.
Pi or 0?
0.
Okay. Tell me why 0 and not pi.
Pi is a -1.
Okay. So when you put that together and solve it, you get t equals 0. Okay, so do you see in that question, it wasn't that obvious at all who the A and the B are, right? You had to actually fight for it. So we now know our integral from t equals 0 to t equals pi upon 2, y, which is this guy, times this guy, this guy's derivative, dt. Now, if you differentiate sine squared, it's a chain rule. You get 2 times sine t times the derivative of the infinite function, which is this guy, dt. And now you've got the integral from 0 to pi upon 2. I've got a 10 here. I have a sine t here. And I have a cos squared t. And I have a dt. So if you differentiate sine squared t, it's 2 times sine t times cosine t. And then there's your dt. Right, I'm not doing this one because I'm getting deja vu. Do you recognize that this is virtually the same as, not quite, but close enough to one that you've already done? Won't it be another u sub, and won't that u sub be cosine t? And dot, 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 dot. Question 8. We're given x equals t squared, take away 2t. We're being told that y equals the square root of t. And we're given a picture that it looks something like this. And we have to find the enclave enclosed by this and the y-axis. So we need to find a start value of t and a finish value of t, and then we can do the rest, right? The rest is waiting for us, right? The bits we need are here. But I need to find a start value of t and a finish value. So I'm going to find what value of t gives you an x equals 0 and a y equals 0. Well, that makes t squared take away 2t has to be 0, and it also makes the square root of t has to be 0. You should be able to do that one in your head. There's only one obvious value of t that makes, are you sure? One value of t that makes both of these 0, and 2 is not it. What could it be if it's not 2?
Zero.
Yes, that may have actually been what you said and I didn't hear it. So that guy there has a t equals 0. This guy up here, oh, come on. I don't know what that value is. Right, it'd be nice if they told me, but I know something about it. Don't I know that its x coordinate is 0? And if I return to this fella, and I pull out t as a common factor, don't I get that t has to be 2? And that guy that I can't read will be the square root of 2, but that's okay. So I now have my start and finish t values. So the area I'm looking for is from t equals 0 to t equals 2. So when you said 2, Lewis, you weren't far away. Y, derivative of this guy, dt. If you want to differentiate something, you have to have strategies. You can't just like wing it. You have to have a kind of idea of what have I got and am I able to integrate it in the way it's looking, right? You know, U sub, for instance, is a good situation where, no, I can't integrate it the way it is right now. I have to do a technique. And this is not a U sub, nor is this, although I guess you could try it, that probably would work eventually, an integration by parts. This is actually some algebra.
So do you actually integrate those two factors and then just do the power rule, right?
Yes. So I'm going to have 3 halves, take away 1 half.
One should be a 2.
What should be a 2?
The negative, so it's 2t minus 2t, or t squared minus 2t that you need to rid of.
Oh, well caught. Thank you. Well caught. Okay, add 1 to the power. Yikes. 5 halves. Divide by the new power is the same as multiplying by 2/5. So that guy gets you 4/5. Add 1 to the power. 3/2. Divide by the new power is the same as multiplying by 2/3, so you get 4/3. Evaluate it at t equals 0 and t equals 2. Now, whenever you're going to be doing an exact value here, it's not a good idea to leave fractional powers for no other reason except for style points. But in this case, this is going to be the square root of t to the 5. And this is going to become 4/3 the square root of t cubed. And by doing that, I will make sure that I'll get an exact value, and I'll get it in a format that we would accept, you know, as style point reasons. So you're going to get 4/5 the square root of 248 1632. Take away 4/3 the square root of 8. Minus a whole load of nothings. So now we're going to introduce you to some algebra. The square root of 32 can be simplified. What will the square root of 32 be simplified into?
16 and 2.
Okay, which gets you 4√2. And the square root of 8 can also be simplified. What does that simplify into?
2 square root 2.
Right? You were right, that one. I just converted it for you. And so what have I got? I've got 16/5 square root of 2. Take away 8/3 square root of 2. Since they both contain square root of 2's, I can just combine them together into a single square root of 2. So I have an ugly 16/5, take away an 8/3, and then you hit math button, choice 1, and it turns into 8/15. And then remember, there's still a square root of 2, and that is the correct answer. They're a little bit messier, aren't they, than derivatives? Aren't derivatives, for the most part, kind of clean, right? You have to kind of, what's the word I'm looking for? You have to kind of fight your way through some of these guys. Any questions so far? Are we okay? Anything bugging you? So now the last piece of the puzzle. We're going to look at the calculus of polar curves. So before we even get into that, I think it'd be a good idea for us to talk about what is polar curves. It's something that you should have met towards the end of calc of 142, pre-calc 2. If you think of a point P in 2D space, there are actually two different ways that we tell people where it is. The first one is called Cartesian, right? You say that's at 3, 2, right? 5, 1, or X, Y. And the second is called polar. And the way that you describe polar is you tell them two numbers. One of the numbers is the distance from the point to the origin. And the second number is the angle that you would need to turn anti-clockwise to reach that point. So you could, for instance, tell someone that the point P was at 5, 30 degrees. You could also tell them it was 5, pi upon 6. Since we are going to be dealing with calculus, we are always going to work with radians because derivatives of trig functions are always done in terms of radians, right? Sure you knew, right? When you do the sine of x, it's a derivative cosine x, but that's only true when x is measured in radians. If x is in degrees, all bets are off. Actually, the answer's not cosine x. So far, so good?
So if they give it to us in degrees, we could just convert it, right?
Yeah, exactly. Hopefully they don't do that, but yeah, if they said from 30 degrees to 60 degrees, you'd have to change it. Now, there is a conversion from one to the other. Can you remember that guy? Right. Can you remember what x squared plus y squared is equal to? Go for it, Jeremy.
1.
No,
Oh, z squared.
no.
R squared.
Yeah, you're bouncing either side. Right, so I kind of know where you were coming from, but that is not, essentially, that's not what we're going to be doing here. Right. So I'm going to go over to Desmos and show you what a polar curve would look like. And then we're simply going to be doing things like finding the area that gets swept when you draw a polar curve. And the reason they call it swept is because it's not like area under a curve in X and Y's. And you imagine starting there and you just sweep like a water sprinkler. How much area would it do as it turns? So that's why they use that term. So here goes. Got parametric? Yes. Oh, wait a minute. I don't want parametric. Hold on. Leave. Go away. Gotcha. There's polar. It's kind of cool. Right, and this is just so you can visualize it. It's not really going to be of any major use to you except to see it perhaps. So what we have here is one that's already set up because that's kind of the way they do it. Let's suppose, so let's just kill these things. I don't really need them. Actually, just kill all of it. And then just do R equals. So when you do a curve, typically a curve in polar format is going to be R equals a function of theta, right? So if I just do R equals theta, there you go. And just like in parametric, I could say I'm only interested in doing it from 0 to maybe 6 pi. And if I zoom out here, can you see it makes a quite interesting spiral? Now, if I integrated this function, right, this curve from 0 to 6 pi, the area I'm getting is, can you imagine the swirl area that you would get from here to here, right? So it would contain all of this, and then it would finish like here, right? So if you're trying to imagine what you're doing, you are finding an integral, but the area is a little bit different than, you know, underneath the X or underneath the Y. It's a little bit messier. Yeah, so how about sine theta? Okay, I'll zoom in. Oh, were you expecting that little circle? In fact, if I wanted to do that, I'm only going to do it from 0 to pi. Oh, do you see the circle is still there? Now, why do you only need 0 to pi? And let's focus in even more. If you imagine starting at the origin, the direction that you go is 0. And then you do these little lines that are basically projecting away from the origin. You can see some of them very faintly. But wouldn't the last one be here? So for this shape, doesn't it go from 0 to pi? Do you see that? You only need 0 to pi. Now, if I add in a cosine of theta, which is this shape here, if you want to draw this shape, right, in polar, if I zoom right in here, there, do you see you only need to go at essentially 45 degrees and 45 degrees that way? So the range of thetas that you would use wouldn't necessarily be 0 to pi. You could get away with different combinations. Right. And I'm getting too much into the drawing of it, which is not something I really feel we need to concern with. So let's do, well, okay, where are you hiding? I've lost me thing. Where are you hiding? Oh, found it. So here you go. If you have a curve, a polar curve, and it's written down as r equals f of theta, right? So it might be r equals 5 cosine theta. It might be theta squared plus 1, right? Whatever it is, right? And you're going from theta equals A to theta equals B. And you want the area that is swept in this movement is the integral from A to B, 1/2 r squared d theta, which in fact is 1/2 f of theta squared d theta. So that's the equation. So as long as you tell me what r is equal to, right, in terms of theta, and you give me a start and a finish value for theta, I can find the area swept out by using this formula. There's not an easy way for me to tell you why that is the formula for the area swept out. So can we go for the, it's true because I tell you, and just call it good. Right. So I'll put it over here so I've got it handy. The area swept by a curve is integral from the start to the finish value of 1/2 f of theta squared d theta. So I've got a question in front of me right now with a nice ugly answer. In question 10, the curve is r equals e to the theta, right? It's got that standard format. You can't really do anything if it's not written as r equals, function of theta. And we're being asked to find the area swept out from theta between here and here. So the area is going to be the integral from 3/4 pi to 3/2 pi, 1/2 this fella here, because he's basically f of theta. This fella here squared. So far, so good. Right? Start to finish. Well, they told me to start to finish. The half, the f of theta. This guy's f of theta squared. Now you got some algebra to deal with. If you take e to the theta and square it, you do not get e to the power of theta squared, right? That's not correct. What do you get when you take e to the theta and you square it?
It would be e to the theta, or 2 theta.
You do. So just think of that guy as e to the 2x dx, if theta bugs you, but theta's okay in my world. I can integrate that. It's not actually that difficult to do, but you have to remember a little bit of a trick. Technically, You could do that as a u sub and make u equals 2 theta, but that's an awful lot of work for very little benefit. So there is a shortcut to it. If you integrate 1/2 e to the 2 theta, you'll get 1/2 e to the 2 theta times somebody. And if you can tell me what you multiply that by, you're pretty much done.
2 theta.
If you were differentiating, that's exactly what you would do. But we are integrating. So you want to change that a little bit, Lewis?
Just 2. No.
With a half. Have you seen that shortcut? It allows you to integrate sine 2x, e to the 2x, you know, things like that. So you integrate it, as you always would, and then you introduce this little times 1/2. If that is a big issue for you and you think, no, I'm not going to be able to remember that, I'm going to confuse it with the rules for differentiation. If you do that, you sub, it'll work. So this guy is 1/4 e to the 2 theta, evaluated at theta equals 3/4 pi and at theta equals 3/2 pi. Well, that's 1/4 e, 2 of them gets you 3 pi. Take away 1/4 e, 2 of them gets you 3/2 pi, and that is your ugly answer. And you could pull out a quarter if you feel like it. Try the next one. This is version of question 11. Let's do r equals 2 over theta squared. And we're going to do from pi upon 2 to pi. And then the area swept out by this curve is the integral from the start value of theta to the finish. 1/2 the function squared. Two times 2 is 4. Half of 4 gets you 2. Theta squared gets me theta to the 4. Right, you got a fraction here. You want to integrate it. I should change the way it looks to allow me to integrate it. How should you write 2 over theta to the power of 4?
Write it as 2 to the theta of -4.
You are on fire. Yes. Now, once you've written it like that, can't we use the power rule? Which is why I wrote it that way, right? And the power rule says, add 1 to the power. Yep, it is -3 when you do that. And divide by the new power. And you're going to evaluate that at theta equals pi upon 2 and finish at theta equals pi. But I'm not going to start plugging anything into here yet. I'm going to rewrite this like that. You want exact values. So when you want exact values, you can't really write down things as pi upon 2 to the power of -3 and think, you know, okay, that's fine, I'll leave it alone, right? Negative powers aren't good for exact values, right? You shouldn't write things down with negative powers, nor should you write things down, you know, with half powers like square roots. So return it to the original style points. Let's see what that gets us. -2 over 3 times pi cubed. Take away -2 over 3 pi over 2 cubed. Well, this guy is pretty ugly. And this guy is 2. Okay, pi over 2 cubed is actually pi cubed over 8. So essentially, we've got 3/8 of pi cubed on the bottom. Agreed? And you might want to say, well, can I leave it like that? No, you can't. You can't have fractions and fractions in them. So I would look at this second term, this one, and just rewrite it as that guy. Are you comfortable about how that 8 made this a 16 and disappeared? Essentially, dividing by 8 is the same as multiplying by 8 on the top, right? And these two can combine, and they look quite pretty. There's your answer.
Nice.
Oh, cool. Nice. So the next one is visual. And I know that you should write down your equations as R equal. And I'm sticking to my guns and saying, yes, you need to do that. And they ask us to do this piece here. Now, I have an integral. I have 1/2. Technically speaking, if I wanted to write this down as R equals, wouldn't it be that guy? But isn't my formula going to square it anyway? So if you wanted to, you could just rewrite it like this and square it, d theta. Or you could save yourself one line of working by just doing that anyway. Are you comfortable with that? Now, we don't know a start value of theta, and we do not know a finish value of theta. But we need to figure out what they are. Now, remember how theta works. If you start at this shape, you're going to start there. And that is a theta of 0. And as you sweep, these projection lines, these radial lines, won't you eventually finish with one that looks like that? So start with theta is 0. And what angle will you finish with if you want to get the second guy? What angle is this?
That's a 90-degree.
90.
Okay.
No, 45.
So in radians, 5.2.
What the hell?
Right. And we're done. I'm not going to do that one with your career. It's pretty straightforward integral. You could do it. Oh, if you want to integrate the sine of 2 theta, won't you get negative the cosine of 2 theta times that ugly a half again, right? And evidently the answer is a half. Go figure. Are we good? Right. So to convince me, I'm going to give you a couple of questions to try it. So x is going to be t squared take away 3t. Y is going to be e to the t. And I want to find the equation of the tangent line at 0, 1. So that's your first question. Your second question is, I want to integrate this function, right, the same one, and I want to integrate it from t equals 0 to t equals 1. And our third question is, R is going to be, what shall I pick? Theta squared plus theta. I'm going to make life easy for you. And theta is going to go from 0 to pi. And I want you to find the integral. You have got 6 minutes, 2 minutes each, to get all 3 guys done. Go for it. No pressure. And I'll remind you, there's our formulas. Should have finished one by now. Got 1 minute. No rush. Okay, that is us. Right, we have 3 questions. I'll take a volunteer who wants to do question 1 start to finish and feels comfortable about doing it. Any volunteers? If you get it wrong, we'll all point our fingers and laugh at you, right? I'm just warning you that up the front. Come on, who wants to have a shot at it? You know, I'm going to do an army voluntold. Okay. Thomas, you've just been voluntold. You want to try it? Okay.
I just did the problem, realized I did it wrong, all wrong.
Well, just say it as we do it then. I'll write down the bits so you don't have time to figure through. So what will the top derivative be? So differentiate e to the t.
E to the t.
Okay. And what's the bottom going to be when you differentiate this?
2t minus 3.
Okay. Now, in this particular question, don't we need to know what value of t generates 0, 1? Right? And there is only one value of t. And did you figure that guy out?
So I determined it to be a 0.
Correct. That's the right one.
And
Okay, so we'll continue with this filler then. So to get the slope of the tangent line, we're going to evaluate the derivative at 0. So that's going to be e to the 0, 2 lots of 0 take away 3. The top is 1 and the bottom is -3. So you're basically working with -1/3. Great. So what do we do next? You don't need to go too specific, but what would be the next step?
I'm just waiting for the screen to catch up on my computer.
So I know the slope of the tangent line is -1/3. And we're after the equation of the tangent line. So what would we do next?
So with
That guy?
your screen's it's catching up, and I'm trying
Oh,
to
I'm sorry.
see what's going on.
I am going to do it for you because it's kind of hard for you to wait every 5 seconds. So y take away y1 is mx minus x1. It's called the point slope equation. So I'll finish off for you. So that's x1 and that is y1, right? The coordinates of the point. So it's going to be y take away 1 is -1/3 x take away 0. And that becomes -1/3 x plus 1. How many of you got that one? Anybody want to stick a little hand up and wave and say, I got that? I'm beginning to feel very lonely here.
I messed it up.
Okay. Well, you
I
tried
think
it.
I messed it up too.
Well, you know, I could
Yeah,
have
same.
messed it up. Are you
I just-
checking that it's not me that messed it up? You got to remember there's a 50-50 chance here.
I just
Um,
found the component, but I haven't plugged it in.
Yeah,
Okay.
that's where I stopped too.
What, not
that
being
is
able
very
to
true.
find, you couldn't figure this guy out? Is that what it was? Okay.
I just kind of forgot the steps after that point.
Okay. Well, you know, this is why we do them. It's easier when you watch me, but you know, when it comes to you have to do it, then you realize, I can't remember what the next step is, or I can't remember how you find this t if you needed to. This one here is the integral from 0 to 1. It's the same function we're going to use. So in this case, it's going to be y of t, the derivative of t dt, right? Poor Tom suffered enough. Have we got any other volunteer to try the integral version of the same question? You lot would be useless in the army, or maybe that's it. You've been in the army and you know never to volunteer.
That's rule number 1.
Okay, so Cam, rule number 2 is don't get noticed. So Cam, you've just been noticed. So here goes. It's 0 to 1. Y of t is this guy. The derivative is 2t take away a 1 dt.
Question, should it be 2t subtracting a 3? Because
I keep doing that. Yes, it should be. Keep an eye on me. Yeah. Right. This guy here will not work with the substitution. Cam, you don't need to get into the details, but what method will I use then to integrate this? Because U subs won't work.
Integration by part.
Oh, we got an integration by parts. Okay. So I'm just going to rewrite it up here. And I like the t's to go first and the other guy to go second. If you're going to do integration by parts, then you make one of your functions f and the other is g. And some of you do integration by parts by doing the udv method, which is totally fine. It works as well. If you do this method, the answer is it's f capital G take away the integral of f dashed capital G dt. And capital G means the integral of this, and f dashed means the derivative of this. So I'm going to take this guy, which is 2t take away 3, integrate e to the t, which is e to the t, take away the derivative of this guy, which is just 2, and the integral of this guy, who's still e to the t. We get that. So I now have 2t take away 3 e to the t. Integrate this, you get.
That would be minus 2 ET, right?
Correct. Yeah. And
Would you be okay?
I'll distribute these, and then I'll collect like terms. And while I'm at it, I'll pull out an e to the t. So this is the integral. You then just evaluate it at 0 and at 1. But if you plug in 1 here, you get 2 take away 5 e to the 1. If you plug in a 0 here, you get 0 take away 5 e to the 0. That's negative 3e, and that's negative of a negative plus 5. And that would be your answer. Negative 3e plus 5, or if you're a purist, 5 take away 3e, which is the same thing. Okay, that was the second. We're almost done. And the third one is pretty much given to you, so you don't need to go hunting for values of t, or for that matter, values of theta. And we're going to do the integral, and it's going to go from 0 to pi, because they told me. And it's going to be 1/2 r squared. And one of these is a theta, right? So it's that guy squared d theta. Does anybody want to tell me what the next line of algebra is going to look like when I come to integrate this fella?
Well, if you FOIL it out, it would be it's theta to the fourth. Well, 1/2 times the theta to the fourth, plus 2 theta third, plus 8 theta squared.
You nailed it. I'm just going to pull that half out. But yeah, who cares? It's going to be ugly no matter what I do, but I'm going to pull it out. As long as it's a constant, you can actually pull halves and fives out. And I got this guy. I'm not saying that's any real help, but for me, it's easier. So, power rule. Add 1 to the power, divide by the new power gets you half. Power rule. It's going to be evaluated at 0 and at pi. This is not going to be pretty. It's going to be 1/5 pi to the 5 plus 1/2 pi to the 4 plus 1/3 pi cubed, take away a whole load of nothings. And I'm looking at this and there's really not anything that nice I can do, but I can pull out a pi cubed, so I might as well do it. So I have 1/5 pi squared plus 1/2 pi plus 1/3, and that is the area swept out by that curve from 0 to pi. Anybody get that, guy? Or at least most of it if you had time? Ran out of time, Cam? Yeah.
I got that. Woo!
Woohoo! Cool. Well done, Caitlin.
Let's just say I messed up the last step.
Right, I mean, there's two kinds of mistake. One is serious and the other is easily fixed. The serious mistake is I don't know what to do, right? I've forgotten the process. I don't know how to do integration by parts, right? I've forgotten how to find the missing t, because if you don't know the missing t, didn't that question like die a death right there at the start, because there's nowhere else to go. And then there's the, I'm calling them the less significant mistakes because I do them all the time. Aren't there the, it should have been +3, but I wrote +1, or whatever it is, a half squared is not a third, right? You know, arithmetic mistakes, writing something down, you know, by misreading it, writing a third when it was 3, those kinds of mistakes. And those are pretty easy to fix. Just being careful. You might wonder how I actually got my degrees with the number of mistakes I make, but believe it or not, I used to have a slightly better brain, but mostly exams bring out the best in me. I was like laser focused when it was an exam, and so I tended to make a lot less mistakes. So what I want to show you for the last few minutes, and so while I'm getting ready, why don't you do the last name attendance thing? Let me get ready here, and we got the guys sorted out. So we've got a video of the beginnings of this. I'm just going to get into a little bit more detail. Our midterm exam is going to be from 5 till 7. And then you get another half hour at the end of that to take pictures of your working and upload it. So I need to see working or it's no good. I also need to see you. So get a video cam, right? Oh God, somebody help me out here because the one I got was a little bit more expensive. But can't you get one less than $100 if you're really pushed? Well, if you're really, really pushed, what's the cheapest bog standard? You know, I don't need HD, right? What's the cheapest webcam going around right now if you hunt for it? Anybody
Go
got an
on
idea?
campus. Go on campus, use the computer lab.
Computer lab works perfectly, right? If all else fails, just nip in there and do it. That works perfectly. Yeah.
Well,
Amazon's got them for like 30 bucks.
Right. So $30 is that kind of, it'll do. It's not great, but it'll do.
well, Walmart has one for like $15.
Okay, we're really getting into cheap. I'm not saying that Walmart might not work. It probably does work. So hopefully it's not a finite. I would feel really bad if I was saying, look, you have to spend $500 now because you need a webcam for this, right? I would have probably changed how we do things if that was the case. So make sure you get it. Here is a list of everything that we are doing. And if you look at the end, we're actually finished. So that means Thursday is going to be review for your midterm. So bring good questions and say, can we go over Taylor series or whatever it might be? Another point, it's been brought up at least 2 different times that when you're doing the, the remainder theorem, find R3 of X, that guy, that your answers are going to be different from WebAssign. Don't worry about it. Once midnight Sunday has sorted out, I'm just going to go back through those questions and give you the points for the, the bit where you find R3 of X, which is f of X, take away T3 of X, the error function. And the decimals that you're going to get are not going to be the same. And the reason for that is that WebAssign is using the algebraic method, right? It's a formula for calculating that error. And we're doing it numerically by just finding the worst case scenario at the end. And I'm okay with that because I really think doing it numerically is more accurate, isn't it? Because you can see where the error is. Whereas if you do the algebraic, it doesn't really care what the function is. It's just a formula that you plug things into and it gives you an answer, but it's not a very pretty formula either. And it's not, in my opinion, as useful, right? So don't worry when you're doing that homework. If every time you get to the R3 or R2, the error function, it's different. And don't worry, right? Put in what you get and then just move on. I'll fix the points later, right? So you won't lose anything. Moving on from that then, we all kind of know don't communicate with any human being during the test. You can use your TI-84. You can use any of the Desmos ones. All of them will be available on the day of the midterm, right? The parametric one, if you want to see things or you want to check things, whatever, they're all going to be there. Everything else will disappear. So you won't be able to watch any videos. Obviously, the practice midterms will all have disappeared as well. So all you'll be left with is a little reduced version. And everything in WebAssign will have disappeared as well. So your job is to get some notes together, right? Anything that you need help on, do that.
Wait, what day does the grid go down? I didn't catch that, sorry.
Everything will go down like 5 minutes, well, give me a break, 10 minutes before the midterm, right? Or half an hour before the midterm. It'll be there until like the last minute kind of thing.
Thank you.
So it won't disappear on Saturday, right? It's not going to happen then. I'm testing this midterm is you proving to me that you know how to do the work, not that you know how to go and look at someone else telling you how to do it and then you duplicate it. If you have to look at a whole load of stuff for every question, you will run out of time. So your notes are there to help you, put down formulas, like if I'm doing the ratio test, maybe you'd have a little example of what the ratio test looks like and what the ratio has to be less than 1 to converge, that kind of thing. But if you have to keep looking, you won't get your time. You won't have enough time. Here's another thing that I want to emphasize. There are no extensions going to be given for week 5. Week 5 is halfway through. Think of it as a door shut. So on midnight on Sunday, the door closes. There is no more homework going to be accepted, right? No extensions. No, well, you never got extensions to test anyway. Nothing will happen. And that is it. So your job is to get as much as that done as you can and find some extra time to get ready for the midterm. Any questions about that before we move on to the next piece? Okay. Now, this guy here that you're looking at, maybe I should make it a bit bigger. Okay, can I do that as a student view? Yeah, it's probably better as a student view. There we go. That's a video that we did last time. It basically just takes you through how to upload your working. That's the PDF that I just spoke about. Here is the link to the Zoom meeting. It will not be our class. It will be that meeting there, right? That's the Zoom one. Click on this guy, and this gives you a video that you can watch that shows you how to use this particular one. If you're using an Android phone, then this is the link. And if you've got an Apple phone, this is the link. And basically it's free. It's a piece of software. Take pictures of your working, upload it. I get it. Now, what do? Well, you upload your working here. And you have half an hour after the exam finishes, right? So you have 2 hours to do your work and half an hour to take the pictures, right, and upload it and all that good stuff. And I've already done this once. You would have that as, you know, assignment or something. You click on it, you upload the file, you choose it, you pick whatever it is called, you hit enter, you submit assignment. And a lot of you will be, can I get out of here? I'm fed up. My brain hurts. Don't leave. Tell me that you've uploaded it. I will go in and check. Because sometimes what happens is there's 8 pages and you've missed one. And I'll say, I can't see question 7. And you'll go, oops. And then you'll have to fix it. But at least I caught it, right? Doesn't happen a lot, but sometimes it's so faint I can't read it. In which case I'll say, could you maybe do it in a darker room or, you know, different angle, whatever, you know, do it again. I can't see it. So this is totally open. If you want to get practice at uploading stuff, it doesn't matter, because when you come to do the test, it will rub out whatever's there and it will put your working in it, right? So it won't be that I'll, you know, I'll have a whole load of nonsense to, you know, search through, right? It overwrites whatever came before. And when you click on this, there better not be a midterm. Good, there's not. Here will be your midterm exam. It will be a PDF. Here's Desmos, parametric Desmos, polar Desmos. This didn't work the last time. I'm keeping my fingers crossed it does, because they're really good notes and I hope that you can use them. If you can't use them directly, maybe it's a Canvas thing. You know, they don't allow certain weird formats to work. You can download it there. And basically, this person has put in a whole load of stuff. This early stuff is all the integration. So if you need some help with integration by parts, of course it's not working right. But if you click on this, after you download it, it will take you and you can actually see it. And she did some really cool work. So here are all our tests. Oh, she even put, I guess, the date that I did them. Taylor's polynomials, cool stuff, right? And
Are we allowed to use these as notes?
as long as you print them.
Right.
They will disappear on the day of the midterm, so they won't be there then. There's an awful lot of stuff there, so remember my rule about it. If you have to fight your way through 50 pages to get to something, you'll run out of time, right? Now, I have no problems with you printing it out. Might be some worth reading, right? Just an aid memoir, just to get your brain as part of your studying. I think it'll be really useful for that. Have we got anything else in that list? Oh, practice. There's one, there's 3 more. They're there for your benefit. I'm going to click on one and I'm going to go to, who shall I go to? Oh, I'm in the solutions, that's fine. Right. Right, look, since I'm here, suppose I tell you that sigma EN and sigma BN are both convergent, right? So they're both convergent series. would sigma AN and BN always converge? True or false? What do you think? If sigma AN converges and sigma BN converges, if you made a series by adding the AN and the BN together, would they also always converge? Now, this isn't math, this is just logic, kind of math, common sense, I guess. What do you think?
Do they actually converge?
Yes, they do. Actually, they converge. Suppose you multiplied them together. Would those two guys converge? And the answer is yes. Oh, you may say, but multiplying things tend to make things bigger. Well, that's true if you multiply two big things together. But if you converge, aren't they going to be two very small things? And don't two very small things, when you multiply them together, make it even smaller? And that's why it would converge. What about dividing? Whoops. What about that one?
I think it'd be false.
Correct. Can you imagine AN and BN were the same function? Wouldn't AN over BN be sigma 1s? Right. Now that's not a test, that's just, mathematical intuition. What do you think about D? First guy squared, take away the second guy squared. Would that converge?
Yes.
Correct. Good thing about that question. Now, when you are doing, oops, excuse me, finishing off here. When you are doing your working, will you try and show me every piece of working you can think of, even if normally you wouldn't do it? And the reason for that, and I'm going to talk a little bit loud because I'm sure they don't want to see here's a conversation. There we go. I can give you partial credit if you do the thing right. Can you remember the one where I put down +1 and it should have been +3? Remember that mistake? Now, if I just kept on going with that number, wouldn't the process be correct? It would be the wrong answer, but it would be correct. But if I'm showing every line of working, imagine you're going to look at that. Won't you be able to say, he wrote a 3, it's pretty obvious, he just didn't pay attention, right? You lose a couple of points. If you go, skip a line, skip 4 lines, answer. If you make a mistake, I've got nothing to give you points for, because all I know is that you got it wrong, and I can't really tell where you got it wrong because I can only see about 2 more lines of working, and maybe one of them's right and the other's wrong, but that's halfway through. And I don't know, if it was a big mistake you made or, something fundamental. So for the midterm and also for the final, will you break your normal habits, which are totally okay for homework? In homework, you cut corners and you miss 2 lines and you do what you want to do because you've got a time issue. But that would be very big piece of advice. Get last questions. Anybody got them? Am I getting so good at this that I've answered every possible question you could think of, or I've turned your brain to to mush because of all the information I've thrown at you in a short time?
You're very
Yes, sir.
scary.
I'm scary. Oh God, no, I'm not. Scary.
Question: do you need to showcase your scratch paper if you did like all your work in there?
So you've got 2 kinds of working I'm picking up here. You've got your lines of working, and then you've got your bit at the side where you just do, I don't know, multiplications or some bits and stuff like that. Is that what you're talking about yet?
Yeah.
That's your choice. I mean, I would probably expect that scratch work won't have anything useful that I could get out of it. So it probably wouldn't matter if you didn't do it. But I mean, I don't know what some people's scratch working is what I would call real working, right? The stuff that you should show me. It depends on what you mean by scratch working. If it's, I don't know, e to the 4 times e to the 3, and you were just doing it at the side to see what it was equal to, that wouldn't be important.
I don't know. I like doing my derivatives on a scrap paper just because sometimes they get really messy. And I don't know. It's like there's a difference between scrap paper and then where I actually show my work or the lines of work.
I need to see those because differentiation is a big deal. Now,
Gotcha.
you can put on each one a big 5 and a line. And this is what I used in question 5. And then 7. And this is what I used for 7. And that would make it at least, I could then look at 5 and say, okay, that's the scratch working or his derivatives for 5 and so on.